Alright, hello everyone, my name is Zach, and in today's video I'm going to be going over how you can solve for the values of A and B in the van der Waals equation of state by using the critical temperature. Alright, so the first thing we're going to do is we're going to hop on over here to this isotherm graph, and basically what this graph is showing you is an experiment is being conducted with a gas, alright, and that gas is being kept at a constant temperature throughout this experiment. So each line represents a specific temperature that the experiment was conducted. Alright, so every line within the graph represents a different temperature. Alright, and basically what is happening is the volume is being changed, and as that volume is being changed, how the pressure changes along with it is what's being measured. Alright, so as you can see here, this TC represents the critical temperature. All right, so this pink line right here represents how the pressure and volume relate to each other at the critical temperature. All right, and these lines up here above the pink represent any temperature that is above the critical temperature, and these blue and kind of sort of violet-y colors down here represent the temperatures that are below the critical temperature. All right, but we are mainly going to be focusing on this pink one right here, the critical temperature line. And basically what we're going to be doing is you can tell that this is the critical temperature because the first derivative and second derivative of this point right here are both going to be equal to 0, alright? No other lines have a point where the first and second derivative are equal to 0, so this is our only critical temperature, alright? And you can tell it is the critical temperature because, as you can see here, the first and second derivative are 0, and what that means is for the first derivative to be 0, the slope has to be 0, alright? So you're going to have just a straight horizontal line, and that is how you can tell that the first derivative is 0. And as you can see right here, the slope is definitely 0, so we can definitely tell that the first derivative is 0. And how you tell that the second derivative is 0 is that it's going to be going concave up, which means it's going to be making like a U shape to the left of it here, and then to the right of it, it's going to be making an upside down U shape, which means it's concave down. So it is also going from concave up to concave down at the same spot, which means that the second derivative is also 0. Alright, so now we know for sure that the first and second derivative of this point right here is 0, so that is going to be our critical temperature. Alright, so basically what we're going to be doing is we are going to be getting the first and second derivative of this equation. We're going to be getting two equations, and we're also going to have two unknowns. We're going to have unknown A and unknown B. And basically what we're going to be doing is we're going to be solving an algebra system of equations to solve for the A and B. And yeah, that's what we're going to be getting into now. Alright, so we are over here at the whiteboard, as you can see, and I've gone ahead and written out the van der Waals equation of state, and what we're going to go ahead and do is we're going to be taking the first and second derivative of this equation, and we're going to be using those equations to solve a system of equations to figure out what A and B are at the critical temperature. Alright, so the first thing we're going to want to do is we're going to want to go ahead and take the first derivative of this equation. So we're going to go dp dv is equal to, we're going to treat these exponents for the v's as a -1 for this one and a -2 when we're taking the derivatives. Alright, so this is going to become negative RT over v minus b squared, right? And then this is going to be plus 2a over v cubed, right? Alright, so there we have our first derivative for the van der Waals equation of state, and we're going to go ahead and set that equal to 0. Because remember, the first derivative and the second derivative of this equation are going to be equal to 0 when you're at the critical temperature, and that is what we're solving for. Alright, so since we're solving for the critical temperature, we're going to go ahead and put a little c in there just so we can remind ourselves that this is for the critical temperature. Alright, and so here we have our first equation. And when we're solving this later, we're just going to go ahead and add this over. So we're going to get 2a over v cubed is going to be equal to RTC over v minus b squared. We would just go ahead and move that one over since this is negative and that's equal to 0. Alright, so there we have our first equation. And now to get our second equation, we're going to go ahead and take the derivative of the derivative, which is going to give us our second derivative for this equation right here. Alright, so we're going to go dp squared over d squared v. That's going to be equal to 2 RTC over v minus b cubed. Alright, and then this is going to be negative 6a over v to the fourth. Alright, so there we go. That is our second derivative. And we're going to go ahead and set this one equal to 0 because remember again, the second derivative is also equal to 0 when you're at the critical temperature for the compound. Alright? And so basically what we're going to do now, we have the two equations we're going to use. The first step to solving this is we're going to divide the first derivative by the second derivative here, alright? Alright, so the first thing we're going to do before we divide the first derivative by the second derivative is we're going to go ahead and rewrite these equations just so they're easier to look at and so we decrease our likelihood of making a mistake, alright? So we're going to go ahead and add this one over to the other side for this equation, and we're going to add this 6a over v cubed onto the other side for this equation, alright? So we are going to get 2a v cubed is equal to RTC over v minus b squared for the first derivative. And for this one, we're going to get 6a v to the fourth, and that's going to be equal to 2 RTC over v minus b cubed. Alright? Alright, here we go. So we are now going to divide the first equation by the second equation, alright? So as you can see here, the v fourth is going to go on top here, and that's going to cancel out the v thirds. So we're going to get, on the left side of the equation, we're going to get v, alright? And the 6a is now going to go on the bottom of this one, so we're going to get a 3. So we're going to get v over 3 for the left side of our equation, right? Alright, for the right side of the equation, the v minus b cubed is going to go on top, and that's going to cancel out the v minus b squared. So we're going to get v minus b on the top. Alright, and then the 2 RTC is going to go on the bottom, and that's going to cancel out the RTC on top, and we'll be left with just the 2 on the bottom. Alright, and now we are going to multiply both sides by 2. And we're going to get 2/3 v is equal to v minus b. Alright, now what we can do here is we can go ahead and add b onto the other side and subtract the 2/3 v. Alright, so we're going to get b is equal to 2/3, actually, excuse me, that's going to be b is equal to v minus 2/3 v, which is going to be equal to 1/3 v. Alright, so there we go. We have now solved for b, so we'll go ahead and write that up top. So b is equal to 1/3 the volume, right? So now we are going to plug this one back into our first derivative for b right here, and we're going to use that to solve for a, alright? So I'm going to go ahead and erase this since we've already used all this to solve for the b. We don't need it anymore. Alright, we'll go ahead and erase this one too. Alright, so now we're going to take this equation, we're going to bring it on down here, and we're going to basically just plug in 1/3 v to b right here. Alright, so we're going to get 2a over v cubed, that's going to be equal to RTC over v minus 1/3 v squared. Alright, so we're just doing some simple algebra here. Plugging in 1/3 v for b, as you can see there. Alright, now we're just going to minus these. This is going to go to 2/3 v, and we're just going to square that. Alright, so we're going to get RTC over 2/3 v, and that's all going to be squared. And then we can just go ahead and square that. That's going to give us 4/9 v squared, so we're going to get that is equal to RTC over 4/9 v squared, like so. Alright, so we're going to go ahead and rewrite this equation so it's not this big jumbled mess over here. So to rewrite that, we're going to go 2a v cubed is going to be equal to RTC over 4/9 v squared. Alright, so now we just have this on the left side and this on the right side. That is the equation. And what we want to do is we want to solve for a, and to do that, we're going to go ahead and cross multiply. So we're going to bring the 4/9 v squared over here to this side and the v cubed over to this side. So we're going to get the 2 times the 4/9 is going to be 8/9, so it's going to be 8/9 v squared a. And then we're going to bring the v cubed over here. It's going to be equal to RTC over v cubed, as you can see there. And now what we're going to do is we're going to divide the 8/9 v squared onto the other side so we can isolate a by itself. So we are going to get a is equal to RTC, and then the 8/9 is going to flip to 9 over 8. And there we have our value for a. Alright, so watching this back, we did make one small mistake in our calculation for a. We did forget to account for these v's here. So what we're going to go ahead and do is we're going to divide the v cubed over here by the v squared, and we're going to end up getting v on this side. So we'll just go ahead and write that in. Alright, so there we have our values for the a and b. Our b is going to be equal to 1/3 times the volume, and our a is going to be equal to the critical temperature times 9/8 times the volume times r, which is just a constant. And yeah, there you have it. Alright, so in the next part of today's video, I'm going to be showing you guys how to solve for the compressibility factor for any compound at its critical temperature. Alright, so here we have our van der Waals equation of state, and I've gone ahead and substituted our values for b right here and our values for a right here that we went ahead and solved in the first part of the video. We have our v over 3 for b and our 9/8 r times the critical temperature times the volume. We substitute that in for a. And over here, we have the equation to find the compressibility factor. The compressibility factor is going to be represented by z, and that is going to be equal to the pressure times the volume over the gas constant times the temperature, right? And we're going to be making this Tc, since this is going to be getting solved for at the critical temperature. Alright, so basically what we're going to be doing here is we are going to be manipulating this equation to solve for p, and then we're going to be plugging in the value that we get right here in for p right here, and we're going to be doing some canceling, and that's going to give us our answer for the compressibility factor for any compound at its critical temperature. Alright, so the first step to solving this is we're going to be doing some canceling. Alright, so we have this v minus v over 3 right here, and we can do that. That's simply going to become 2/3 v right there. And we also have this v over here on the other side, and this v squared over here in the denominator, so we can cancel those out, and this v is going to go away, and this is simply going to come v down here. Alright, so we'll go ahead and write that out. Alright, so that's going to become RTC over 2/3 v, and over here the v's are going to cancel out, so it's going to be 9/8 RTC over v, right? And we can move some of these fractions around just so it's easier to look at. So we're going to go 3 RTC over 2v minus 9 RTC over 8v. Alright, we're just doing that so it's easier to look at. Alright, and here we can see we can multiply this side right here by 4 over 4. So that we can get this to have a common denominator, so we can subtract out these. Alright, so we want to get both of the denominators to be 8v and 8v, so we can subtract the numerators over here. So we're going to go ahead and multiply the left side by 4 over 4. So we're going to get 12 RTC over 8v, and that's going to be equal to, this one right here is not changing, that's going to stay how it is, that's going to be minus 9 RTC over 8V. Alright, and as you can see here, this is basically 12 RTC over 8V minus 9 RTC over 8V, and that is simply going to simplify down to 3 RTC over 8V. Alright, so we're going to go ahead and write that out. 3 RTC over 8V. And there we go. That is that's going to be the pressure at the critical temperature for any compound right there. Alright, so now that we've solved for our P, we're going to go ahead and plug this in right here for our P up here. So we're going to get Z is equal to, and we're going to go ahead and write this in where we should be writing P. So we're going to go 3R times the critical temperature over 8 times the volume, and we're going to be multiplying that by V. Go ahead and get some parentheses around there. And that's going to be all over R times the critical temperature, since we are solving this at the critical temperature, alright? And as you can see right here, we have a volume over here, and we have a volume in the denominator over here, so the volumes are going to be canceling out, like so. And then we have an RTC up here and an RTC down here, and those are going to cancel out as well. So basically, all we're going to be left with is a 3 over 8. Write a better 8 there. And that is going to be our answer right there. That is going to be the compressibility factor. And that is for any compound at its critical temperature, alright? So this isn't going to change at all. If you get any substance at its critical temperature, this is going to be its compressibility factor right there. Alright, that is going to be all for today. Make sure to smash like and subscribe, and have a good one.